Welcome to the video for the last couple of pages of the section 2.1 notes. Here at the bottom, page 6, we're going to look at example 12, a piecewise function. And we're being asked to determine the limit of this piecewise function for a couple of x values, when x is approaching 3, when x is approaching 1, and to do so algebraically. Now remember, when you are determining limits, you do want to consider left and right-hand limits. And you want to make sure they equal each other. So let's start with part A. The limit as x approaches 3 of f of x. Well, when x is approaching 3, we're clearly going to be in this region when x is greater than or equal to 1. And if you do the graph, actually down here, at x equals 1, we get 1. X equals 2, we get 0. X equals 3, looks like we get negative 3. And there you go. The other one's a linear function, 1 I sub of 2. If I plug in 1, I get 0. Plug in negative 1, I get 4. And you get something that looks like this. So just looking at the graph, I suspect that I'm approaching 3 from the left, approaching 3 from the right. Excuse me. Excuse me. That they're going to converge, and I could just do a straight up substitution. So the limit as x approaches 3 of 2x minus x squared, so it's 2 times 3 minus 3 squared, 6 minus 9, I get negative 3. So that's pretty simple. Now B is going to be a little bit tricky. You want the limit as x approaches 1 of f of x. Now in this case, when x is approaching 1, yes, when x equals 1, we do equal this function, but it's not about equal, it's about approach. And we look at the left and right sides. From the left side, we see that we got to use, like when x is slightly less than 1, we're going to have to use a negative 2x plus 2 function. For the right side, we have to use the quadratic function. So when I do my LHL, so the limit as x approaches 1 from the left of f of x, so in this case, x is approximately like 0.9 or 0.999 and so forth. I'm clearly using this inequality because obviously the x values are less than 1 when I'm doing the left-hand limit as x approaches 1. So I'm doing negative 2 times 1 plus 2, which is 0. Here for my RHL, I'm taking the limit as x approaches 1 from the right. So in this case, x could be approximately like 1.1 or 1.01. So of course, x is a little bit bigger than 1, so I'm using the 2x minus x squared. So 2 times 1 minus 1 squared, that's going to be 1. Clearly, the LHL does not equal to RHL. So the limit does not exist. And graphically, we see that over here. From the left side, we're going towards 0, but the right side, we're going towards 1. They don't link up. So you do have to be very careful with piecewise functions, especially if x is approaching a number that is part of these boundaries here for those inequalities. But for A, that was just fine. You just look at 2x minus x squared because you're just in that region, so that's not a problem. But for B, we did have a problem, and we had to be very mindful about the LHL and RHLs. Let's keep moving. Okay, now we're going to talk about trigonometry. So here we have sine x over x. The limit as x approaches 0. We're not going to do the formal proof, but we will investigate this graphically and numerically. So in your TI-84 calculator, you can plug in sine x over x, or you can do it in Desmos if you like. If you do the TI-84 calculator, after you punch in sine x over x, make sure you're in radian mode. So hit mode and make sure you select radian. And then in window, go and type in negative 4 pi and 4 pi for x min, x max respectively, and make the scale pi. That's going to make the graph kind of reasonable to investigate. And the y min and y max, negative 1 and 2, y scale 1, x res, don't worry about that so much. So that's going to be, if I scroll down just a tad. So here's negative 1. and 1 and 2. And here's negative 4 pi, negative 2 pi, negative 3 pi, negative pi, pi, 2 pi, 3 pi, 4 pi. And we're going to graph it. So I'll get my graph calculator. You should probably do the same for yourself at home or wherever you are. So mode, radian, clear whatever I got there, sine x, divide by x, negative 4 pi, 4 pi, pi, negative 1, 2, graph it. So you get something that kind of looks like this. And there's going to be a hole right here, just so you know. In Desmos, actually, it will show it as a hole if you get closer to it. But if you hit second trace, and then select option 1, which is value, and type in x equals 0, the calculator is not going to give you a y value. It's just going to have like a y equals and a blank. Of course, I'll have x equals 0. So that means there's a hole there. But the limit will exist because the left-hand limit and the right-hand limit both approach 1. Our LHL and RHL graphically show that we're getting closer to 1. So that's going to be the value of our limit. It's going to be 1. Numerically, what you could do is plug in values close to 0, like 0.1 or negative 0.1 or 0.01 or negative 0.01. And you're going to see that same thing will happen, that will get closer and closer to the number 1. So if you were to actually quit out, if you hit alpha trace y1, 0.1, so if you hit alpha trace and then y1, and typed in 0.1 or so forth, you should get something that gets very, very close to 1, like 0.998 or whatever, something like that. So we see that this is a true statement, that sine x, the limit as x approaches 0, sine x over x is 1. What if we change mode to degrees? Well, if I do go to mode and do degree, and if you try graphing it, I don't believe you're going to see anything in the graph. And that's because the scale doesn't work for us anymore. You won't see the graph at all. If you could try resetting the window, but again, you're not going to really see much. And so, very important that we stick with radian mode. The reason why is that when we do the formal proof of the limits as x approaches 0 sine x over x, the formal proof assumes radian mode. So that's why we have to do that. Okay, we're at the last page. Let's look at tan x over x. So if I do a substitution, now remember, tan x is sine x over cosine x. We know this from our pre-calculus classes. It's one of the main identities that you should know. So you could do a little rearrangement here. You could write this as a limit as x approaches 0, sine x over cos x, and that's of course x over 1. And you can flip over the x over 1 because it is a division. And so you could also keep rearranging and write like this: sine x over x times 1 over cosine x. And then you can actually use one of our properties, the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. Well, here's the deal. This right here equals 1. And this right here is also going to equal 1 because you could just substitute straight up. 1 over cosine 0 is 1 over 1, which of course is 1. Well, 1 times 1 is 1, so the answer for this is 1. So whenever we see tan x over x and the limit as x approaches 0, we can make that assumption. And what we just did over here, or over here, I guess, kind of exemplifies this property. A times B over C equals A over C times B over 1, or equals A over 1 times B over C. So it's somewhat interchangeable with multiplication. That's kind of what I just did here. I just did a little rearrangement of fractions. Like, for example, 4/3 times 2 is the same thing as 4 over 1 times 2/3, right? They're the same thing. You know, no different. So that's something you could do. We'll keep moving. Now, example 14 is going to be pretty close to something you're going to see in worksheet 4 for homework. You do see a piecewise function situation, which I'll give you some hints. But like number 4 or 5 and 6 will kind of help you if you take a look at example 14 here. So we're going to do a little rearrangement. We could think of this as 3x times sine x over x squared plus 5x squared over x squared. So you can break up the fractions, just like we see over here. Totally legit thing you can do. This case, you can't really do any breaking up. But like, for example, if I had like 4 plus 5 over 7, that's the same thing as 4 sevens plus 5 sevens, right? So that's exactly what I'm doing here. And of course, I'm taking the limit as x approaches 0 of all this. Then I could do a reduction. 5x squared over x squared is 5. And I could do a reduction here. 3 times sine x over x. And again, the limit as x approaches 0. Well, guess what? What's the limit as x approaches 0? 5. 5. What's the limit of as x approaches 0 sine x over x? We know it's 1, but as you're multiplying by 3. So essentially doing 3 times 1 plus 5, and the answer is going to be 8. And you could, if you so desire, go to Desmos and actually plug in this actual function here and see what happens when x gets close to 0, and you should be able to get that to work out for you. So if I were to go to Desmos, if I were to do y equals 3x sine x plus 5x squared, make sure I put that in parentheses, divided by x squared. And if I scroll up, you can see that there is a hole at 0,8, but before and afterwards, we are approaching 8. So you can always check your work using Desmos. But you want to be a little creative, like breaking up fractions is a good idea. And then kind of at the home stretch here, what if I have something like this here? Something that looks a little funky, sine 5x over 5x. Well, you could do a little kind of trickery. Let a equal 5x. If you do that, you have the limit as x approaches 0 of sine a over a. Of course, that's a problem. X, of course, is a over 5. So you could just say, hey, I'm taking the limits as a approaches 0, because it's going to be kind of the same thing. And that's still going to be 1. So it didn't really matter so much that, you know, we have 5x over 5x or a over a. Whenever these are identical and you're doing a sign, your limit's still going to be 1. And you can actually graph that in Desmos and see for yourself. So by doing a little trickery, letting a equal 5x, so you have sine a over a, but of course x approaches 0 doesn't make any sense. A equals 5x, so x equals a over 5. If x is approaching 0, of course a is also approaching 0. And you just, you know, work it out. And you're going to get the same thing over here as well. It'll still be 1. So generally speaking, if you have sine kx over kx, the limit will just be 1. Now in this case, this is going to be a little different. Again, we'll let a equal 9x. And actually, you could probably do something a little different here. Actually, let's backtrack a tad. No, actually, that's fine. We'll let a equal 9x. So of course, x is a over 9. So in this case, I have the limit as x approaches 0 of sine a and a over 9. So what happens is that the limit, and actually there should be a is approaching 0. Because remember, if x is approaching 0, a over 5 is also approaching 0. If a over 5 is approaching 0, a is approaching 0. So in this case, if x is approaching 0, a over 9 is approaching 0. If a over 9 is approaching 0, of course, a is approaching 0. So I'll be, I can flip this over. So I have 9 times sine a over a as a approaches 0. Well, I know that's just going to be 9 times 1. And I get 9. So in this case, we have sine of kx over x. The limit as x approaches 0. The answer is just going to be k. So that's kind of another property we got there too. So on the worksheet, for worksheet 4, you're going to want to break up some fractions. We do see sine 2x over x, so we'll have to, you know, use that property we just saw over here. Sometimes you could just straight up substitute if that works. Here you can see an opportunity to break up fractions. You could do this over x minus this over x. Over here you have to get a little creative. 5x squared, remember, is 5 times x times x. You could probably do sine 3x over x. You could probably do e7x over 5. And you could probably do tan x over x. Because when you decompose this big fraction into 3 smaller fractions, but then it's a product, it's still the same thing. And of course, you do the limit as x approaches 0, of course. Easy enough. And you just work each of those out. So I kind of given you a hint of how to do 6. Don't do 7 and 8. We already did those in worksheet 3. Those are repetitive, so don't worry about 7 and 8. If you want to do them again, that's great, but you don't have to. Number 4, we kind of just did, that's like example 14, I believe. Kind of like that one a little bit. And of course, 2 and 3 are like example, I believe 11 that we did in class last time we met. So, and then this one here is kind of similar to what we did with root absolute of x over x. And of course, writing as a piecewise function, which you should be comfortable doing, but I'll kind of give that to you. As a piecewise function, it's going to be x minus 3 over x minus 3, assuming that x is greater than 3, or you can say greater than or equal to 3 if you like. And then it'll be negative x plus 3 over x minus 3, assuming x is less than 3, that this part is holding a negative value. So I replace x, I multiply x minus 3 by negative 1 to counteract that. But of course, if I realize that, oh yeah, x minus 3 over x minus 3 is 1, negative x plus 3 over x minus 3 is negative 1, This is what's happening. So there we go. And I think we're all squared away. So that's the end of the video. And then you'll do a worksheet 4 for homework, and there'll be some textbook problems as well that I'll put in Schoology. Have a good weekend. Oh, and I was correct in my prediction. I think I had 34-21 Chiefs for the Texans. Score was 34-20. So I know you're impressed. Okay, see you later.